So I think we can start. It's already 3 o'clock. So I welcome all the students on this live interactive session on chemical and thermodynamics. So it's week 10 and week 10 is already over. So we'll look out for all the contents, some numerical and the associated assignment problems related to the week 10. So a very good afternoon to one and all. So this is live interactive session on NPTEL online certification course on chemical engineering thermodynamics. Just a quick view. So this course has been offered by Professor Gargi Das, she is a professor in the Department of Chemical Engineering at IITKGP. And like a little bit about myself, as I am the teaching assistant. Myself is Shubham Majikowama, and I am a PMR scholar in the Department of Chemical Engineering at IIT Madras. So like we have been going through all these live interactive sessions till now, and today is we are going to discuss related to the week 10. So we have already surpassed till week 9, and 2 more weeks we have to go to the final examinations. So apart from week 10, we will be having week 11th and week 12 for the final examinations. So what I've been saying is that it's better. I will suggest to all the students, please look for all the live interactive sessions we have. All the videos have been uploaded on the NPTEL One portal, and it's also on the YouTube. You can go anytime and just have a quick view. Apart from that, all this PPT, what I've been discussing, the problems or the contents of the week has been uploaded in the form of a PDF in the NPTEL One portal. So what we will do is that in the week 10, since we have like 3 weeks to go through, we'll have like some of the contents to cover up. As of now, till week 9, we have been covering on like from the ideal non-ideal solutions, activity non-activity coefficients, and some of the problems related to that. So the last week we have discussed some of those problems related to assignment and tutorial for the ideal and non-ideal solutions and deviation from the ideality in the terms of solution. And we also seen some of the like PTXY diagram and TXY diagram for the solutions, and how you can identify using if they give different problems to you, different problems in the terms, they give different plots to you. You need to identify which forms an isotopic mixture or like maximum volume isotope or minimum volume isotope. Just by looking at a diagram, you can say okay, it deviates positively from the ideality or negative from the ideality. From that, on the basis of that, you can identify the the isotopic compositions. And how to separate these isotopes we have already discussed in week 8 and week 9. So today, week 10, what we're going to do is that we will discuss. So the week outline for the week 10 content is somewhat like this. So the first one is the thermodynamic consistency test for VLE data. So this is thing that is we already discussed in the week, like I've been discussing for the past few weeks from the week 7 itself, and the non-ideal and non-ideal solutions have started. Okay, that's known as thermodynamic consistency for vapor liquid equilibrium data. The second thing is partial and complete immiscibility of liquid mixtures. So this thing also we have been covering up from the past week. I have shown this content related to the form of the plots. So there are like different plots which discuss if you say you have a two binary mixture, they forms an immiscible mixture or a miscible system. So miscible in the sense they are soluble into each other, and immiscible in the simple terms are they are insoluble into each other. And how this immiscibility and miscibility will affect the vapor liquid equilibrium data we have discussed in the last week. Okay, the third one is the phase equilibrium transfer for the mass transfer processes. So this is somewhat like a newest topic, and I think this is not discussed in like a broader content as of now, but we'll see what we have been covered in this. So what I will do, I will just go through some of the contents that has been covered during the week 10th and the week 9th as well, and we'll start solving some of the numerical problems related to that. Okay. Before starting, I would like some of the formulae which will be helpful for ours. Okay. Now, since we have covered like ideal and non-ideal, both the gases and the solutions, so we'll write some of the things. So just for a quick understanding, for an ideal gas mixture, you know mu I is now the chemical potential for an ideal gas, and the excess gives free energy in an ideal gas solution is given by RTLN YI. Okay. Similarly, for an ideal solution, gas or liquid, we have mu of Ig is equal to G of Id is equal to G of Id plus RT ln Xi. So Xi is a mole fraction of the components in the liquid phase, whereas Yi is a mole fraction of the components in the vapor of the gas phase. Okay, so these two are the two different things you need to remember, guys. Okay, now another thing is how to identify which are the ideal solutions. So properties of ideal solutions. So V of ID is Vi. Similarly, enthalpy of an ideal solution is the enthalpy of the component I in the mixture, and similarly entropy of an ideal solution mixture is the entropy I minus RLN Xi. Now since you know that the partial molar or the mixture properties, so we write total property is the summation of Xi mi bar. Okay, so these are some of the things or the formula which I will suggest please be remembered to the, because this will be helpful in the final examinations content also. Okay, now another thing we have covered is known as the rules. So first one is Lewis Randall rule, and the second one is the Henry. So Lewis Randall rules can be written as viscosity of component I in the ideal solution is given by mole fraction of component I in the liquid phase into the viscosity of the component I in that mixture. Similarly, the viscosity coefficient is given by phi. Okay, now the excess property, the another term which we have been covering through many of the times. Is given by the excess molar property is given by the molar property and the molar property of an excess property of an ideal solution. Now for an ideal solution, if you take the excess property is 0. Okay, so this is one thing. Another one formula that I would like you guys to remember is like the excess gives free energy, or the excess property gives free energy is given by RT ln Fi cap into Xi Fi square to RT ln gamma I, where this gamma I is nothing but the activity coefficient, and of the component I is given by Fi cap on Xi Fi. Okay, so this is the things that I wanted to discuss with you guys. Also, if you take the excess gift free energy in terms of like thermodynamic consistency is given by Gibbs-Strom equation, I can say summation of Xi and then gamma I, and if I take summation of Xi taking partial differentiation of excess gives me energy equal to 0, this implies summation of Xi d ln gamma I equal to 0. Okay, now another thing that the main thing which you have to remember is some of the property relationships and the excess molar properties. So I'll just quickly read some of the formulas for that also, which has already been covered in the week content. Excess property relations. So if you take the excess gives G is equal to H minus Ts, so the excess gives free energy is G is equal to He minus Tse. Similarly, is equal to Similarly, enthalpy, excess property of enthalpy relation can H equal to U plus PV, right? So U E plus, and similarly Okay, and we have covered like different non-ideal solutions equations. So I'll just mention that equations. So the equations are known as, so first we have covered um, Margulis or Margulis equation. Then we have 2 suffix and 3 suffix. We have covered NRTL, non-random 2 liquid equations. So, and we have Van Laar. So these are some of the equations in which we have solved numericals in the last week. So what I suggest, if no one has gone through that week content, please go first through it, because I have solved some of the equations and the numericals related to the non-ideal solutions, just to identify the activity coefficient. So these are known as none other than the activity coefficient models. Okay, just to identify the value of gamma 1 and gamma 2. So in order to identify the value of gamma 1 and gamma 2, we have used like different activity coefficient models. First is Margulis, 2 suffix, 3 suffix, Van Laar equation, and non-random 2 liquid equations. And we have solved some of the numericals. It will give during the examinations, identify the value of the activity coefficient gamma 1 and gamma 2 using the parameters given in the questions. You need to identify which equation you have to use. Predominantly we will use Van Laar equation, because I solved in the last week using Van Laar. But it's up to you, because in some of the equations they specifically specify the value of gamma 1 and gamma 2 using NRTL. So at that time you have to use NRTL equation. There will be 2 different parameters coming up, like G12 and G21, and similarly in Margulis 2 suffix and 3 suffix, ln gamma 1 and ln gamma 2. So please go through the week content. We have already solved some of the numericals, and we have also mentioned the formula there for all these 3 equations for the activity coefficient models to identify the value of activity coefficient 1 and activity coefficient 2, that is gamma 1 and gamma 2. Okay, so this is the thing that I wanted to cover up as far as the content is discussed. Now what we will do is that we will go and solve some of the numericals which I wanted you guys to have a look at it. Okay, so we'll just quickly go through the first question. So if you see the first question, so n-heptane and toluene forms an ideal solution. So it has been given the 2 components. Say n-heptane is a component 1 and toluene is a component 2, forms an ideal solution. So at a temperature of 373 Kelvin, that is at 100 degrees Celsius, the vapor pressure is P1 and P2. So set P, vapor pressure of 1, vapor pressure of 2 is in kilopascal. Determine the composition of liquid and vapor in equilibrium at temperature is this, and pressure is, that is 1 atmosphere, 101.325 kilopascal. So it's the simplest question, but I will try to solve out. So now since we have been given 2 components and the forms a solution, that is an ideal. So what is the total pressure of the system? So the total pressure of the system will be x1 P1, vapor pressure of 1, plus x2 P2s. Okay, now since x1 plus x2 equal to 1, the total mole fraction will be 100%, that is 1. Now we have been given, we have not been given x1 and x2. What we will do, we will place x2s 1 minus x1. Therefore, simplifying the equation will give x1 P1 set, x2 is equal to 1 minus x1 P2 set. On simplifying this, we will have P2 saturation plus P1s minus P2s x1. So we put all this value of P1 and P2. So P2 is, so total pressure is 101.3 equal to x1 okay, this is P2 is 74 plus 106 minus 74 into x1. So from here you can identify the value of x1. It comes out to be, so if you solve this using a scientific calculator, it comes out to be 0.853. Okay, now we know that y into p is equal to xi into saturation. Okay, so I'll write in terms of first component, where p is the total pressure, x1 equal to p1 set. Therefore y1 comes out to be x1 p1 saturation upon p total 0.853 into p1 is 106 divided by 101.325. Therefore y1 comes out to be 0.893. Okay, so this is the answer. So this is the simplest one. Just need to identify how to find out the total pressure of the system. So if you have like different components given, so you should know, okay, the one component is there, two components, they have been given the vapor pressure and they've given the temperature, everything. Just need to identify what the total pressure of the system will be, the sum of the components of the individual vapor pressure of the contributing to that system. Okay, so this x1 p1 side plus x2 p2 side is equal to total pressure pt. Okay. Now since the components are in a solution, the total mole fraction will be terms equal to 1. So x1 plus x2 equal to 1. So now you can replace x2 or x1, whichever you want to like. Like suppose I replace x2 with 1 minus x1 up here. So similarly, you can replace x1 by, what I can say, 1 minus x2. Okay, so it's depend upon your choice. So you can identify, if you want to find out the x2, so x2 will be 1 minus x1, so x1 will be 1 minus x2. So it's like vice versa, it's just depending upon your choice. Okay, so this is the like the simplest question. We move to the next one now. So here what is given to us is that an equimolar solution. So here also there are two components which forms an equimolar solution. That is, if you take equimolar means distributed equally. So we will have like 0.5, 0.5. So benzene and toluene are given to us, which forms an equimolar. So we'll take 1, 2 is totally evaporated at a constant temperature of 363. So temperature is given as 363. Okay. At this temperature, the vapor pressure of benzene and toluene are this. Okay. So this is given P1 saturation, P2 saturation. What are the pressure at the beginning and at the end of vaporization process? So this one is also like the similar to last one, but here you need to find the initial and the final pressure of the vaporization process. So we'll take, oh sorry, benzene as component 1, toluene as component 2. Now since they forms an equimolar mixture, so what we'll have, x1 equal to x2 equal to 0.5. Okay, now also we know that total pressure will be x1 p1 side plus x2 p2 side. So in times of pt is x1 is 0.5, 135.4 is p1, x2 is 0.5, p2 is 54. And therefore pt turns out to be 94.7 kilopascal. So this is at the beginning. This is the pressure, total pressure at the beginning of the evaporation process. Now we have the mole fraction x can be given as, if I simplify that equation, and similarly y so what I can find out the total pressure in terms of, so I'm simplifying these equations. So what I will do now is that, so how did I find out this one is, since yi is equal to xi into psi divided by total pressure. Okay, so this is the Raoult's law from now. So we have an equimolar mixture, right? So at the end, what will be? So put y as 0.5, and we have like P1 set, P2 set, P1, P1, P2. Put all these values in this equation. We'll just find out the value of Pt, and it turns out to be 77.2 kilopascal. So this is at the end. Okay. So this is the simplest one. Just need to type rearrange the total pressure equation and can identify the initial pressure and the final pressure at the beginning and the end of the vaporization process. Okay. Yeah. So this is good. We'll quickly move on to the other question. So this is also like we have been continuing, like, because why I'm solving these equations is that, so these are not like lengthy types. I don't want to go to the lengthy type numericals because I don't think so. It will be if it's like 2 marks or like if an MCQ form. These are the simplest type questions that can be asked in the two types, like the previous two questions which we have solved. If it's in a lengthy type, it can be in the form of like activity coefficient models, like Van equation, marvelous 2 suffix 3 suffix, or non-random two liquid equations. Okay, so quickly go on to the next question. So even after looking at the question, I can say, okay, this is related to somewhat of the Antoine equations. So these are known as Antoine equations because given as ln of p set is equal to a minus b upon t plus c. Okay, where a, b, and c are the Antoine constants, and if specifically if in the examination it will be given, but in some of the like universities examinations, so like in my university exams, we used to get this not even the equation, they will say use Antoine equations and find the value of such a vapor pressure of A and B. Okay, so if you know what is Antoine equation and the temperature, now you to identify the value of A, B, and C. Even they will not give the value of A, B, and C in some of the university examinations. So what you have to do is that you first have to look out what is the component A or the component B that has been given in the question. Suppose A is like benzene. So for benzene, the internal constants at that particular temperature and pressure will be given in the supplement in the sense appendix. So in appendix, at the extreme end of every book in like in chemical and in thermodynamics, if you say extreme thermodynamics, there are appendix like in F or G appendix. It will be there. I think so. I don't exactly remember which appendix alphabetical order is there, but it's there, which mentions the Antoine constants. And if you know the temperature, pressure conditions, and the component name, you can find out the value of A, B, and C from that. So during our examinations, it used to be like that, but in the like in MCQs or in the GATE examinations, NPTEL examinations, I think they will give you these equations directly, and just you can identify the value of final answer. Okay, so we'll go quickly and see what is asked in the question. So mixture of A and B conforms closely to Raoult's law. Okay, the pure component vapor pressure and A and B at temperature Kelvin is given by this. That is the Antoine equation given to us. So if the bubble point of certain mixture of A and B is 349 Kelvin and a pressure of 80 kilopascal, find the composition of its four vapors that forms. Okay, we need to find out the first vapor, composition of the first vapor that forms, that is what. Okay, so temperature is given to, okay, temperature is 349. So what we'll do at a temperature of 349 Kelvin, we'll find out vapor pressure of A, sorry, 14.27 minus 2945. Similarly, 14.60 minus 29. So just find out the value of PA from here and PB from here. So it's just nothing, you have to solve the right hand side and take the exponential of that term, because LHS and the ln will go on the opposite side, it turns into exponential. So it turns out to be 85.9128 kilopascal and 43.3116 kilopascal. Okay, now we know the vapor pressure of A and B. Now what we'll do, since we need to find out the fraction of the vapor phase that form, so x1 equal to, I'm not writing the total pressure equation, I'm just writing a simplified form, P minus so total pressure is going to assess 80 pascal, so this is PT. Okay, so we'll write 80 and we have P2 as 43.3116, P1 is 85.9128 minus 43.3116. This comes out to be 0.8612. Okay, therefore if I take x1 is equal to xa is equal to 0.8612. Now ya is equal to xa is going to give to us, so this I will take it from ya is equal to xi psi upon pt. Okay, so we need to find out the value of ya. Xi is 0.8612, pa is 85.9128, total pressure is 80 is equal to 0.9249. This is ya. Okay, so this is the answer which has been asked to identify the composition of this first vapor forms. So the composition will be 0.9249. Okay, so this is like the simplest one. Using this Antoine equation, we identify the value of vapor pressure of A, vapor pressure of B, and they have used the total pressure equation, that is PT is equal to x1 P1 set x2 plus x2 P2 set, and we have simplified this equation and find out the value of x1. Then we have used the Raoult's law, and then we have found out the value of the vapor composition, that is y1 or ya. Okay, so we'll move to the next one. This one is like the similar to the last one, but here something is different. So if you see what has been given, so the vapor pressure of acetone and acetonitrile, so there are two different components. The one is acetone, the second one is acetonitrile, can be evaluated using the Antoine equations. So this is 1 Antoine and this is 2, and we have been given Antoine constants A, B and C already in the equation. So where T is in Kelvin and the pressure is in kilopascal, assume that the solutions forms are ideal. Okay, and calculate x1 and y1 at temperature of this and pressure of this. Okay, this is similar to that one. So just like for practicing it's good, but okay, what we'll do, we'll find out 14.5463 2940.46, temperature is 327 minus 35.93. Just solve this one, and similarly ln of P2 set is equal to 14.2724 minus 2945.47 divided by 49.15. So if you solve these two equations, the value will come out to be this is 85.12 kilopascal and this is 39.31 kilopascal. So just you have to take the ln on the right hand side and it will be exponential. Okay, now since we this is similar to the last one only, and we know that x1 plus x2 equal to 1. We have not value of x1 and x2. So what we'll do is that we'll simplify this. X2 as 1 minus x1 So we have been given total pressure of 65 kilopascal. X1 we do. Uh, to further simplify this one, we will have like uh, X1 uh, 85, that is P1 minus P2 plus P2. Okay, so from this X1 comes out to be 0.5608. So this is what I have simplified and I have written, that is X1 P1 set minus P2 set plus P2 set. Okay, now we'll use the Rao's law. This implies, so this is x2 equal to 1 minus x1, since x1 plus x2 equal to 1. Okay, therefore y1 is equal to this is the total pressure 0.5608 25.12, the other total pressure is 65. Solving this, we will get 0.734. Yeah. So this is the answer for vapor composition. This is the answer for the liquid composition. So this is the simplest one, how to identify using the vapor fraction compositions. Now in the examinations, since these are the simplest ones, so what they will do is that they will ask you to find out these compositions. Along with these compositions, they will ask you to find out the various parameters. Suppose if this this can also be used to find out that in the activity coefficient models also. Okay, so in activity coefficient models, you just need to know which model you have to use, because all the models have different equations and different constants. Like Mendel constant different from the marvelous 2 suffix marvelous 3 suffix constant a and b, which are known as the constants. So I will request you guys to please go through the week 9 lecture content and the live interactive sessions we have during the last week, because I have solved some of the numericals related to the Mendel equations and Mendel constants and how to identify the constants on that. Okay. So I am trying the similar questions again and again, is that just to get familiarized with all the things, because if you don't know even the simplest question how to solve, so it will be difficult for you to the bigger questions to arrive at. Okay, so we'll solve this bigger one here. So it's somewhat different related to the previous one what we are solving as of now. So from vapor liquid equilibrium measurements of ethanol benzene systems, so if you take like ethanol benzene, so just like classify as 1 and 2 at a temperature of 318 Kelvin. So this is the temperature and the pressure of 40.25 kilopascal. It is found that the vapor is in equilibrium with the liquid containing this mole fraction of the benzene and this mole fraction of this might be ethanol, sorry. Okay, it's printing mistake. Okay, and 56.6 mole percent of benzene. The system forms an azeotropic. Now the main thing around here is that at 318 Kelvin it forms an azeotrope. So like I said, we have discussed and what are isotopes and why they are formed and how to separate the isotopes from each other. So isotopes are none other than the close boiling mixtures. So if I give you two components, suppose here what they have mentioned is that ethanol and benzene they are taking as a system, and the forms and isotopes means they start boiling equally at 318 Kelvin. Okay, now how to separate this, because the board will start evaporating at 380 Kelvin and you can't able to separate using that in the distillation column. So because both of the vapors in the enrichment vapor and enriched vapor goes at above, in which have the both compositions of ethanol as well as benzene. Now if I want ethanol and benzene to be separated, but how to break this isotope? So in order to break the isotopes, we will use two different types of system which have like antenna or a solvent. Okay, so this instead of one distillation column, there will be two distillation columns. So in first distillation column, along with the feed of ethanol benzene system, we will add an antenna or a solvent. So what this antenna solvent will do, it will contain some part of its highly enriched vapors of it, like more volatile component. Suppose if I take ethanol as a more volatile component, it will take antenna along with the ethanol to the top part, it will condense, and that condensate is sent to another distillation column. So in second distillation column, what will have that ethanol will come from the top and the ethane will come from the bottom, and this ethanol can be recycled back to the first distillation column for continuous process. So this is how you break an azeotrope and an azeotropic mixture, and how you can separate an azeotropic mixture. Similarly, we can use different solvents which are compatible with this, because it will be miscible with one of the component and immiscible with another. Miscible means in the sense it will be soluble with one of the components but not soluble with other. So in which it is soluble, it will take that component along with it is in the condensate part, and which is not soluble, it will retain as a residue, that is an raffinate part from the bottom of the distillation column. Okay, so this is how, like we already discussed on the content. Please go through that contents also. Now, so they said that at this temperature the vapor pressure of ethanol and benzene are this one, that is P1 set and P2 set are given. Determine the composition and total pressure of the azeotrope, assuming Van equation is applicable. Okay, here comes the activity coefficient model. It is Van equation. So what we will do, we will take okay, let me take benzene as just for sake of ease. Benzene is component 1, ethanol. You can take whatever you want. You can take ethanol as component 1, benzene as component 2. Okay, so I will take benzene as component 1, ethanol as component 2, and the vapor pressure of 1 and 2 is given as 29.6. So 1 is benzene, okay, remember that. Temperature is given 380 Kelvin. Total pressure is 40.25 kilopascal. And azeotropic temperature, that the temperature they forms an azeotropic is the same, that is at 318 Kelvin. Now we know that the mole fraction is also given, so x1 equal to 38.4, 56.6. Now what we'll do is we find out the value of the activity. I think this is okay. The system forms as at this temperature the vapor pressure of ethanol and benzene are this and this. Yeah, okay, this is good. So what we'll do is to find out the value of the activity coefficients gamma and gamma 2 using the Van law. So gamma 1 is equal to, I'll just use the values directly, that is 0.566 into, that is 40.25 is the total pressure, upon x1 is 0.384 into, where is it, the P1 side is 29.6. Similarly, x2 equal to 0.4 remaining one is 0.434 into 40.25 total pressure divided by 0.616 into 22.9. So this is what I have taken from the mole fraction components that have been given to us. So if you calculate this values, it turns out to be 2.00 somewhat, and this is 1.238. Okay, now what they have been asked is to use the Van law equations. Okay, so Van law, therefore T equal to ln gamma 1 plus x2 ln gamma 2 upon x1 ln gamma 1 whole square. We'll put all the values here. So ln gamma 1, so I'll take gamma 1 value as 2.00 and put ln of that, it will turns out to be 0.6953. 1 plus x2 is 0.616 into ln gamma 2. So gamma 2 value we have as 1.238. We'll put ln of that, it turns out to be 2137. And similarly 0.6953. Similarly we have v equal to ln gamma 2 x2 is 0.616 into ln gamma 2 is 0.2137. So you can find out the value of a p from the Bohr equation. So a comes out to be 1.54 and 1.95. Now we have to find out compositions, right? Composition and the total pressure. So what we'll do, we have total pressure P is equal to gamma 1 P1 set and P is equal to gamma 2 P2 set. Therefore gamma 1 is equal to P upon P1 set and gamma 2 is equal to total pressure upon P2 set. So this is what I have used. So now we have to do trial and error method. Okay, we don't know the values of G1, G2, gamma 1, gamma 2 and isotopic close to each other. So what we'll do is that we'll try to assume some values. So let's assume, x equal to 0.4 to 0.6. G1 and G2 we don't know. So what I will guys to suggest is that since this will take a longer time to solve, what I will suggest is that you guys take a value of x1 or the x, like the composition in the liquid phase as 0.4 to 0.6, and try to solve out the values of gamma 1 and gamma 2. Use the values of A and B that we have identified and try to solve out the value of x1 and y1. So just take like the number of iterations you will try to arrive at a final answer, because they haven't given as an isotope. So that is close to each other. Okay, temperature is close to. So it will take like one or more two steps to iterate and arrive at the final answer for x1 and x2. Okay, just try it out. If you're not able to solve it out, we'll discuss in the next week live interactive sessions. Okay, so it's just for a practice. Like since if I try to solve it out everything, it will be difficult, because I don't think so none of the students will try to have a hand-on experience on how to arrive at a final answer. Just like looking at the numericals and looking at the solutions doesn't make any sense. I suggest everyone please do have a look to these numericals what I've been solving from the starting to the end, and please do have like a hand-on experience. Take some answer numericals from any reference books, even in some of the like NPTEL assignments problems. Take the problems. Don't even look at the solutions. Even if it's what you solve is the wrong one, don't worry about the wrong solutions or the wrong answers. It's what matter is that how you are solving the numerical. Doesn't worry if the final answer will be wrong or not. It matters with the fact that the steps which you are following is systematic. Okay, because once you know how to solve systematically the questions and the answers, the answer doesn't matter at all. Okay, so in the final examinations also, all that thing matters. Even in the university's exams, I have seen it many times, as I have been reading many of them. So what we'll look at is the systematic way. Even if we have solved like some of the numericals in systematic manner, it doesn't look even for the final answer. Even the final answer varies from like 50 to 60%. But this some of the students have solved systematically in a proper manner and they have used the proper approach to arrive at a final answer. It might be a mistake of some numerical, not like a digital, not a digital, the decimal error or some numerical error in the calculations. But the method they arrived at the final answer is correct. So we probably give the full answers to that, full marks to that. It's not we look at the final answer only. So what I'll say is that please solve it systematically. Identify which thing you have to solve, which equation you have to use, why you have to use this equation. That also has to be specified first. Okay. So please look into that things. Now what we'll do is that we'll use solve one more numerical similar to like the last some of the methods we've been trying to solve. Okay, so this is the same question. So I will not solve it again. What I will do is that I will tell you guys how to do it. So see, this is similarly Anthony. This is equation 1, equation 2. Try to solve this method because I know definitely this type of questions will be there in the final examinations or in the gate one. In gate examinations, this type of questions will be asked numerous number of times. It's not just like the simplest one to identify the total pressure, but way above that, so it counts to be like 2 to 3 marks. Okay, so what is given is that x1 is 0.55, x2 is 0.45, total pressure is zero point 0.7 bar. We need to find out the temperature. Temperature is not given. So in the previous questions, we need to find out is what we are doing is to find out the value of vapor pressure of component A and vapor pressure of component B. Now here we need to find out the temperature. Okay, so what we'll do is that 1 into P is equal to x1 and y2 equal to P is equal to x2 to set. And we have ln of P1 set given to us, and we have ln of P2 set given to us, but we don't have the value of the temperature. So this is x1, this is x2, with the equal as 0.7 bar. Also, what we can do is that we have like y1 plus y2 equal to 1. Similarly, we have x1 plus x2 equal to 1. So what you have to do is that solve the above equations to get the unknown variables y1, y2, similarly x1, x2. So these are the unknown variables. Okay. So we have been given pressure. Find out the value of the compositions, that the liquid phase composition x1. If you find out the value of x1, so x1 plus x2 equal to 1. So x2 will be 1 minus x1. Similarly, y1 plus y2 equal to 1. That will, if you take y2 is equal to 1 minus y1. So using the total pressure like PT is equal to x1 to insert plus x2 to set, we have solved like 3 to 4 numericals in the starting of this lab and tech sessions. Try to solve it out using this equation in this case also, and find out the value of x1, x2, y1, y2. Use this value of x1, y1, x2, y2 to find out the saturation pressure, because you can use the find out the saturation pressure from here. Okay, P1 set and P2 set. So once you have like P1 set, P2 set, put these values up here. The only thing you need to identify is the value of temperature. Everything is known. So in order to find out the vapor pressure of component 1 and vapor pressure of component 2, first find out the mole fraction of the components x1, x2, y1, y2 using the total pressure system, because we have been given mole fraction. Okay. Okay, sorry, x1, x2 is already given. You need to find out the value of y1 and y2. So that's okay. So once that's solved, find out the value of vapor pressure P1, P2. Use this P1 set, P2 set in this Antoine equation, and you can identify the value of this. Now here also there is a trial and error. This is not a trial and error. Just put the values in that equation and find out the value of T. Okay. So if we solve this, the temperature will come out to be, I am writing the final answer, that is 340 Kelvin. P1 set. Okay, I also write the value of y1 and y2. Okay, just try to solve it out. You will arrive at these answers. I mentioned answers to you, but I have not shown the strategy to solve because I want you guys to solve some of the numericals on your own. Okay, so this is one of the things similar to the first three questions, but here the tricky thing is you need to find out the temperature, not the temperature, along with that the values of the vapor pressure of component 1 and 2. Okay, please try to solve it out. It's not like the toughest one. Is the simplest. Just need to find out the value of two different things up here. There are two different unknowns, and then the temperature and the set vapor pressure of 1 and 2. So we move to the last question of today, and this is somewhat related to the what I can say is activity coefficient models. Like we have solved some numericals which can be related to the Van Laar and Van Laar constants NB, but we have not solved some of the simplest activity coefficient model is like you can say marvelous 2 suffix or 3 suffix. So what I'll do, we will use marvelous 2 suffix equation in order to find out this answer. Okay, so what has been given to us is the infinite dilution activity coefficient of a liquid mixture of isopropanol 1 and water is given to us as 1 and 2. So isopropanol is one component, second component is water, and they form a liquid mixture. And they have given the infinite dilute activity coefficients at 320 Kelvin, that is gamma 1 and gamma 2. Using the marvelous 2 suffix or marvelous equation to describe the excess Gibbs-free energy of this mixture, at this temperature, the vapor pressure of 1 and 2 are 150 and 79 mm of mercury respectively. A liquid mixture containing 60 mole percentage of isopropanol, so 0.6, and x1 is 0.6, x2 is 0.4, is in equilibrium and its vapor is temperature 320. The mole fraction of isopropanol in the vapor phase. Okay, so we have to find out the value of y1. Okay, so what we will do is that we will write out what is given to us. So it's better because this, if you see this type of the questions, it will be too much lengthy, like 4 to 5 different lines, and there are so many data given up in the questions. So what I have suggested is that try to write down the values of what has been given in the question, then I get the final answer. Okay, so given is temperature is 320 Kelvin, P1 set is 150 mm of Hg, P2 set is 79 Hg, gamma 1 infinity is equal to 1.5, gamma 2 infinity is equal to 3.5, x1 equal to 0.6, x2 equal to 0.4. We need to find out the value of y1. Okay, so according to Raoult's law, we have like y1 into p is equal to x1 P1 set and y2 equal to p is equal to x2 p2 set. And from Margol's equation, we have ln gamma 1 infinity is equal to a12 and ln gamma 2 infinity is equal to a21. Okay, where so we find the value of a12 is equal to ln of gamma 1 infinity ln 0.5 a21 is equal to ln of okay. Now we have marvelous So put all the values in this equation what you have solved. This will comes out to 0.162, 0.793. Okay, so gamma 1 will be exponential of 0.162 and gamma 2 will be exponential of 0.793. Which comes out to be 1.176 and gamma 2 is 2.211. Now since we have y1 into p is equal to x1 gamma 1 p1 set, so you can notify the value of 105.9. and similarly y2 into p is equal to x2 gamma 2 p2 set. So put the value of x1. Similarly we have gamma 1 gamma 2, we have x1 x2, we have p1 p2. So we use this equation, therefore y1 equal to x1 gamma 1 p1 set by total pressure is equal to 1050.9 where the total pressure is 175.7. So it comes out to be 0.6. So this is the final answer. Okay. So this is how we use the marvelous surface equation in order to find out the vapor fraction composition of the system. Okay. So this is what I have for today for this week 10 live interactive session. I know it's going like a quicker review because we are left only with the 2 more week contents for the final exam to get started. So if you have any issues related to the assignments and tutorial problems, please do ask me in the live interactive sessions itself. I will request every student who is taking this course on the NPTEL, please go through all the free contents as well as the assignments and the tutorial problems. Along with it, please also go through the PPTs that have been uploaded. That what we are interacting is uploaded in the form of a PDF, and all these videos have been recorded and uploaded on the YouTube, and the links will be provided in the NPTEL Swim portal. So please go through that. If you have any issues related to any big content problems that we have solved during the assignment, this live interactive sessions, or any assignment problems, or any other problems related to some of the like unsolved problems we have been trying to solve or taking some of the from the friends books, please do ask me in this advanced live interactive sessions. I will be happy to help you out. Okay. So if none of you have any questions, we'll call it off for the day, and we'll meet you next week for the week 11 live interactive session on Saturday from 3 to 5. Till then, thank you for joining this live interactive session for today. Thank you, guys. We'll meet you next week, 3 o'clock. Thank you.